So the very first slide, these are the energy levels of hydrogen. You'll notice on the left side we've got these n numbers, n equal 1. That's the ground state. That's the minimum energy an electron can have. This is kind of the bottom rung of the ladder in the ladder analogy. This is the this is the energy state that every electron really wants to be in. Right? Then there's n equal 2 is a big jump, n equal 3 is a smaller jump, 4 is a smaller jump, and they keep getting smaller and smaller and smaller until finally you get to the infinitieth energy level. You say, well, okay, let's keep going. We've got absorption. Absorption in this particular arrow is from n equal 2 to n equal 4. So the second rung on the ladder to the fourth rung on the ladder. Absorption is the name given any time an electron moves from a lower energy level to a higher energy level. It is not only between 2 and 4. It could be between any two levels as long as the electron is gaining energy. So that's absorption. Emission, in this case, it's from 3 to 1, but again, emission can be from any higher energy level to any lower energy level, and it does not have to go all the way down to the ground state. If you went from 3 to 2, that's still emission. Right? Finally, ionization. You'll notice that ionization completely removes the electron from the atom. In other words, the electron gets so much energy that it gets boosted past the infinitieth energy level, which means it's no longer part of the atom. We'll get into more detail on this in chapter 12 if we get that far. Again, this is showing the electron starting in the ground state, but it could be starting in any state. Ionization simply means the electron absorbs enough energy that it leaves the atom entirely. So what you're looking at here are a series of we're not going to get into this very much. You don't have to know these names like Paschen, Balmer, and Lyman. These are people who discovered these ground states around 100 years ago, or pardon me, discovered these transitions about 100 years ago. But you don't have to know what they are. I guess one thing that you should appreciate here is that these large changes, these large absorptions and emissions represent ultraviolet, which is a lot of energy. The smaller absorption and emissions represent visible light, which is less energy than ultraviolet. And these smallest absorptions and emissions represent infrared, which is the least amount of energy among these three. Finally, over here, you don't need to know these values, so you can ignore those values. This slide brings up an important idea. The difference between something that's continuous and something that's quantized. Let me set this up just a little bit with the previous picture. Before we said that if you have an electron in a particular state, let's just say the ground state, it can't absorb any amount of energy. It has to absorb a specific amount of energy. In other words, it has to absorb exactly enough energy to go into the second energy state. Or it has to absorb exactly enough energy to go into the third energy state. It cannot absorb a photon of light that would put it somewhere in between here or somewhere in between here. That's simply not allowed by nature, right? Or doesn't appear to be. What that means is that the energy levels of hydrogen are quantized. There is a precise amount of energy that will get you into the second energy state. No other amount will do. There is a precise amount of energy that will get you into the third energy state. No other amount will do. So what does that have to do with this? Well, what that means to say that something is quantized means it comes in discrete amounts. This ball can fall from one step to another, but it always has to land on the step beneath it. It can't hover in the air between two steps. So if somebody says to you, "Where is the ball?" you could tell them exactly which step it's on, right? Continuous is different. In a continuous, here the ball can be at any position it wants to be, right? And so if somebody says, "Where's the ball?" you can't give them, you could give them a precise location, but that precise location could be anywhere, as opposed to quantized, where if somebody asks you, "Where's the ball?" it has to be exactly on one of the steps and it will never be in between. You say, but yeah, what if I stop keto when it's falling, but it hasn't landed on the next step yet? This is where we bump up against quantum mechanics. In the world that you and I live in, or in the world that we understand and experience, sometimes that's called the macroscopic world, the world of big things. The ball actually does have to fall from one step to the next, and so it does make sense to say, where's that ball, right? That's not the case in quantum mechanics. That is not the way electrons appear to experience the world. An electron that is in the ground state transitions or moves to the first excited state instantaneously without ever passing in between. That's hard for you and I to understand and appreciate and even just flat out believe, but 100 years of evidence, experimental evidence, suggests that's very much literally true. It's not an analogy, it's not an approximation. It's not even just that our experiments aren't good enough. It's not like it's happening too fast and we just miss it for reasons that we're certainly not going to get into in this class. It is instantaneous, right? And so it is truly quantized. The ball stops being here and starts being on a different step instantaneously, right? So you'll have to know what these two words mean. Here's the way it works. Anytime you transition down, anytime you fall to a lower energy state, you've got to emit light, and that light has to have a specific amount of energy. What we're going to start doing, instead of talking about energies, we're going to talk about color, because it turns out those two words are interchangeable in this chapter. So the thing to take away here is that the smallest change in energy emits the least amount, the reddest light. Right? Red light has the least amount of energy. If you fall further, if you have a bigger change in energy, now you have green, right? Because green has a little more energy. Green has more energy than red. You fall even further. Well, now it's bluish purple, right? Because this end of the spectrum this end of the visible spectrum has the most energy. You say, well, what if I fall even further and it goes beyond purple? Well, how do you say beyond violet? Ultraviolet. Now you're emitting ultraviolet light. You and I can't see it, but we certainly believe it's real, right? You'll stand out in the sun for 5 hours with your shirt off and tell me if it's not real. You say, well, what if I go this far? What if I have such a small transition that it's beyond the red? Well, the way you say beyond red is infrared, and that's going to be heat. So the thing to take away here is that when we look at these transitions, what you and I are going to see, or the way you and I will experience that transition, is by seeing color. And you say, well, wait a minute, kid. When I see something glowing red, the coils in a toaster, the coils on the oven, coals in a fire, you're telling me all of that light is coming from electrons falling from higher energy? Yes. Yes, yes, yes. That's exactly where the color. If it glows, electrons are falling, right? From high energy, an excited state, to lower energy. In this case, it's showing the first excited state. It could be the ground state, but it's falling to a lower energy state. So we make maps of this, right? We talk about the spectra. On top, of course, we have Roy G. Biv, all the colors of visible light. This, in the middle, is called an absorption spectra. These blank black lines represent specific amounts of energy, or specific colors of light, those two mean the same thing, that have been absorbed by a molecule or a gas. On the bottom, we have the emission spectra. Once that atom or gas has been sufficiently energized, it will now emit these precise colors of light. You say, well, do the black lines on the absorption spectra always have to match up with the emission spectra? And the answer is yes, they do. Yes, they do. So if you were to shine a light through a gas, you would see all these black lines if you had a spectrometer, if you had a machine that could look at these spectra. If you got the gas hot enough to glow, you would see the corresponding colors that are missing from the rainbow up here. So the emission spectra will always have these lines in it, right, that represent the specific transitions of electrons from one particular energy level to another particular energy level. And these lines are unique to each material. And so what we're seeing here, for example, is the emission spectrum of hydrogen. This is the fingerprint of hydrogen. This is how God or nature says hydrogen, these colors. All you have to do is add one more electron to make helium. Well, technically you have to add a proton and two new, but in terms of the electron cloud, all you're doing is adding one more electron, and all of a sudden you've got a completely different range of colors, right? This is the fingerprint for helium. This yellow line right here is what was discovered in the sun about 100 years ago when helium was discovered in the sun's outer atmosphere during a full solar eclipse. That's where the name helium comes from the Greek god Helios. Ooh, jeepers, study there, Cato. Here's how you would actually do that. You would have your source of white light, right? You shine it through a slit, and then it hits a prism. And as you very well know, that prism is going to break the white light into Roy G. Biv, a rainbow. If you're looking at a rainbow in the sky, this prism is actually just fine drops of mist, right? Fine drops of water. But you might have one of these bits of cut glass hanging from windows in your house, or something like that, where they're creating rainbows when the sun shines through them. Now you take a particular gas. Now, if we were at school, I would show you for a particular, just a sealed tube that has hydrogen in it. In outer space, it's not sealed, but it's just a big cloud of hydrogen gas. Shine it through the slit, let it hit the prism, and now instead of Roy G. Biv, you only see the colors. You're only seeing, where to go? You're only seeing this, right? If it happens to be helium, you see this. Now, if it were a mixture of hydrogen and helium, that gets a little more complicated because you're seeing both of these. But thousands and thousands of hours have been done, of work have been put into finding the spectra of individual elements and learning how to tease them apart, right? You say, well, why would we ever want to do that? Here's one reason. We can look at the spectra. We can look at the light shining through the atmospheres of planets going around other stars. Those are called exoplanets. And we are just learning how to figure out the molecules that are in the atmospheres of these planets using this technique. Let's look at this I'm going to biggen this just a little bit here. So what we're looking at, this is a particular exoplanet. Here's point 1. And at point 1, you can see we're getting mostly, all this tan color is light from the star. This darker orange is light coming from the planet. There's just a tiny amount of light coming from the planet at point number 1. At point number 2, there's nothing, right? Because we're seeing the dark side of the planet that's not illuminated. At point 3, we get this big dip, and you say, what's happening here? Well, the exoplanet's passing in front of the star, isn't it? It's blocking some of the light from the star, and that can give us information about the planet. Now, I should say the data you're looking at here is pretty clean. In real life, there's quite a lot more to it than this. And then as we go from 4 to 5 to 6 to 7 to 8 to 9, you can see that the planet becomes more and more illuminated, gets brighter and brighter until finally, bloop, what's happening at 9? Well, it's passing behind the star, isn't it? The planet is passing behind the star, and we can't see its light anymore. And that tells us a bit about the planet as well. All of this dark orange light right here is light from the planet, right? And all of that light is going to have the signatures of molecules in the planet's atmosphere imprinted on it. And if we can learn to read this light, if we can use this process so that instead of a high voltage tube of hydrogen gas, if this light is coming from the atmosphere, this is the dark orange, coming from the atmosphere of the exoplanet, all we have to do is send it through a prism. It's not going to be this clean. It's going to be much, much more complicated. But we're clever and we're determined, and we'll learn to read that light and figure out what atoms and molecules are in the planet's atmosphere. And that's pretty exciting, because one day when we find oxygen, that's going to mean we have found life on a planet going around another star.